So we've got a question here about horizontal resisted motion. It's going to follow the same format as most resisted motion questions. We're going to have to write down the forces equation to start with, and then we'll have to see how we go there in terms of our integrations and what we're asked to find. So after crossing the finishing line at a speed of 5.5 metres per second, a rowboat glides to a stop. The drag created by the water, the skin drag, is 1/10 of mv squared. And the drag created by the shape of the boat, the form drag, is 100 of mv. Find v as a function of x. And hence, find the distance that the boat glides before stopping. Okay, so let's write down the force equation. It's always a good place to start. So the force equation, the forces that are happening, we've got the mass of the boat times its acceleration is equal to the resistance that's happening to it. So we've got minus of 1/10 mv squared, and we've got minus of 1/100 mv. So if we let the direction the boat's going after it crosses the finish line and starts gliding along, we let that direction be the positive direction, then these two forces are resisting the motion, so they're in the negative direction. And that's the total force on the boat, because the rowers aren't rowing anymore, and the normal force due to gravity and gravity just cancel each other vertically. So horizontally, that's all that's going on. You can see we can divide out the m here. So that would make things look a bit easier. X double dot is equal to, divide out the m, and we get minus 1/10 v squared minus 100 v. All right, now we need to integrate. So what we can do, we could use d dx of a half v squared, or we could use v dv dx. Now looking ahead, v dv dx is looking like a good idea, because if I have v times dv dx on the left, I've already got some v's on the right. I can divide through by the v's, because we know the velocity is not zero, right? And then I can get a simpler equation. So I'm going to do that. I'm going to do v dv dx, because I've been asked to find v as a function of x. v dv dx is minus 1/10 v minus 1/100. V squared minus 1/100 v. Then I'm going to divide by v. So that'll give me the v dx equals minus 1/10 of v minus 1/100. All right, so I'd like to take from there, and I'd like to go ahead and integrate that. So I'll need a bit of room over here. So I was at the point where dv dx is equal to minus 1/100 into 10v plus 1. That's basically what I've got. Minus 1/100 into 10v plus 1. I just factorised it out and made it look a bit easier. Now I'm going to do an integral, but first I'll do a bit of rearranging. So I've got dv on 10v plus 1 equals minus dx on 100. So that's not too bad to integrate. When I go to integrate it, if the derivative of 10v plus 1 is 10, so I'd like to have a 10 on the top. So I might pinch a 10 from down here. So this will be 10 dv on 10v plus 1 equals minus dx on 10. All right, so now I'm going to integrate those, this and this, and I end up with the natural log of 10v plus 1 is equal to minus x on 10 plus c. Now, when we go back to the original question, the question said you're crossing the finishing line at a speed of 5.5 meters per second. So when x is 0, because this is when the situation starts, we want to know how far it glides, right? So x is 0 is the finish line. The velocity is 5.5. So if we pop in 5.5 there and 0 there, we're able to say that c is equal to the natural log of 55 plus 1. C is equal to the natural log of 56. Therefore, C equals the natural log of 56. So I'm pretty close to getting the answer of find V as a function of X. I'm pretty close. So what I'll do is I'll write down that ln of 10V plus 1 equals minus x on 10 plus ln of 56. Let's get these ln's together and do a bit of, log arithmetic here. ln of 10v plus 1 minus ln of 56 equals minus x on 10. So that's ln of 10v plus 1 on 56 equals minus x on 10. Because I want to get v equals some function of x, I'm going to raise each side to like e to the power of the left and e to the power of the right. If I do that, I'll get 10v plus 1 on 56 equals e to the negative x on 10. So 10v plus 1 equals 56 e to the negative x on 10. So v will end up equaling 56 e to the negative x on 10 minus 1, and all that is times by 1/10. So there's v equals 1/10 of 56 e to the negative x on 10 plus 1, minus 1. So I've got the first part that the question said. It said find v as a function of x. Now it said hence find the distance that the boat glides before stopping. Now, we know that it will never stop under these circumstances, and I might have an investigation of that in a minute, but really we just want to put 0 in for the velocity and see what value we get for x. So I'll do that. I'll just need a little bit more room. Let's put 0 in for the velocity. 0 equals 1/10 56 e to the negative x on 10 minus 1. So that means 56 e to the negative x on 10 equals 1. So e to the negative x on 10 equals 1 on 56. So e to the x on 10 equals 56. So x on, if we take the log of both sides, x on 10 equals the natural log of 56. So x equals 10 times the natural log of 56, whatever number that is. Just going to whack that in the calculator to get some idea how far it glides after the race. 10 times the natural log of 56 goes about 40.25 metres, roughly, right? Approximately 40.25 metres. Now, like I said, that there is a limiting distance. Like technically, by the maths, it would never get there, but we know that the reality is it would actually get to that stop. But I want to show maybe by deriving x as a function of t, how if we make t go to infinity, like we look at the limit as t approaches infinity, maybe we can see that x approaches 40.25, or 10 the natural log of 56. So I'll need a bit of room to do that, and I'll need to start with my velocity equation, because that's dx dt. So if I integrate that, I can get x as a function of t. So I'm going to start with that, and I'm going to integrate that in order to find x as a function of t. So I need a little bit of room. That's why I'm just heading back here to this spot. And about this point that I look at the camera and go, have I turned the camera on? Because that would be, for you, you'd probably be happy because you'd be, oh, finished. But for me, just done all that work and I've got to do it again. So I want to start off with this equation, and I want to get an equation in terms of x and t. So v is equal to 1/10 56 e to the minus x on 10 minus 1. So that's dx dt equals your 1/10 56 e to the minus x on 10 minus 1. All right, so that says dx on 56 e to the minus x on 10 minus 1 equals dt on 10. So this is where we need to use our skills in integrating. And I think sometimes trying multiplying everything by e to the 2x, or e to the 2x on 10, or e to the x on 10, or e to the minus x on 10, and seeing what happens. Because I'd like to actually have an e on the top, because an e on the top can be a derivative of the e on the bottom. So I'm going to try timesing everything there by e to the x on 10. I think that's going to work out nicely. So on the top line, I'll end up with e to the x on 10. And on the bottom line, I've got 56e to the minus x on 10, and I'm timesing by e to the x on 10. And then I've got minus 1, and I'm timesing by e to the x on 10. So I've times the top and the bottom by everything by e to the x on 10 there. So then I get over here, and that's got my dx still, and that's my dt on 10. So this is looking good because it's e to the x on 10 all over 56, and that'll be e to the 0, which is 1, minus e to the x on 10. Now, if I just had, this will differentiate to minus 1/10 e to the x on 10. So I need minus 1/10 to be put up there. Yes, that's what I need to do. I need minus 1/10 here. So if I times that by minus 1/10, I'll times this other side here by minus 1/10 as well. And that will get that working pretty well. So give myself a bit of room here to keep on with my integral. I'm going to leave that answer there that I found before. Now, the top, the derivative of the bottom is sitting on top of it there. So if that should have a dx, if I now integrate this side and integrate that side, I'm going to get the natural log of 56 minus e to the x on 10 equals minus t on 100 plus c. Now, when t equals 0, x equals 0. So that's e to the 0, which is 1. 56 minus 1 is 55. So c is the natural log of 55. Because when t equals 0, x equals 0, and you plonk them in there. So our equation is natural log of 56 minus e to the x on 10 equals negative t on 100 plus natural log of 55. Let's do a bit of natural log arithmetic again. Like we want to get this e to the x by itself there. So we've got natural log of 56 minus e to the x on 10, and it'd be minus natural log of 55. So that will be divided by 55, and that's equal to negative t on 100. And now we will go take e to the both sides. So this will be 56 minus e to the x on 10 on 55 equals e to the minus t on 100. And then we need to do a bit of arithmetic now. We've got to try and get e by itself here. So let's just have our minus e to the x on 10 is equal to 55 e to the negative t on 100 minus 56. And now we need to move across to get a bit more room to finalise the whole thing. So here, this is e to the x on 10 equals 56 minus 55 e to the minus t on 100. So I just times both sides by minus 1 to make it easier. So I take the natural log of both sides and I get x on 10 equals natural log of 56 minus 55 e to the minus t on 100. So x equals 10 times the natural log of 56 minus 55 e to the minus t on 100. Now, as t approaches infinity, we've got e to the minus t on 100. Now, we know what e to the minus t looks like. E to the minus t is going like that. So as you head out that way, this term here is becoming towards 0 as t approaches infinity, which means 55 times 0, 0, which means we've got 10 ln 56, which is the 40.25 that we found before. Now you could graph this on Desmos and it would look like a function coming up and limiting itself at, it would look like a function something like this, where this is 10 ln 56, which is an asymptote here, and our distance goes from 0 up to 10 ln 56 as time goes on. If you put that in Desmos, that's probably what the picture would look like. But you weren't asked to have to do that. So you were able to go way back to just keeping v as a function of x to get the answer. That's what the question said. But it was worth further investigating that to understand it more fully and also to make sure this was a 20-minute long video.